Hey class, let's check out some vocab and graphing of rational functions by looking at domain, vertical asymptotes, and horizontal asymptotes. Let's start with a first example of f of x and we'll put that equal to 3x plus 2 over 2x minus 1. First, let's discuss domain. Domain is the set of all x values that you could sub into this function, and it will crank out some kind of value. It turns out, for your domain of rational functions, you want to look at your denominator and find out what makes it 0. Remember, dividing by 0 is one of the big no-nos in mathematics. So for this particular problem, that's when 2x equals 1 or x equals 1/2. Now, since we don't want that to be 0 in the denominator, we're going to record our domain as all real numbers except for 1/2. We want all the good guys, in other words. Vertical asymptotes occur at values of x where the denominator is 0, as long as the denominator in factored form can't be canceled out by a factor in the numerator. Now, since 2x minus 1 doesn't have anything in the numerator to cancel it, there's not another 2x minus 1 factor, then the vertical asymptote will be located at x equals 1/2. So those two concepts of domain and vertical asymptote, you have to be very careful. In domain, you don't want the denominator to be 0. With a vertical asymptote, you look for where the denominator is 0 as long as the factor in the denominator can't be canceled away. Horizontal asymptote, you look at your original function. If your values of x have the same dominant exponent, for example, in this one, both numerator and denominator have a power of 1 for the x term. Those are the dominant terms from top and bottom. If those tie, then your horizontal asymptote will be the ratio of those two terms coefficient. So that's going to give us y equals 3/2. When we graph, we are going to put a vertical boundary up at x equals 1/2. A vertical asymptote is like a vertical force field that your graph can't pass through. The horizontal asymptote, your graph can pass through it, but the importance of it is where your graph has x values that are extremely large or small, your graph will flatten out at that horizontal asymptote. Now, you can assist yourself with a graphing calculator by typing in the original function. Please feel free to do that. In fact, I'm going to do that on my graphing calculator just to be extra sure. I'm going to do parentheses 3x plus 2, closed, divide, open another set for the denominator, and when I graph, your graph will be flat on the far left and far right sides, which is expected, and looks something like this. If you wanted to be extra careful and plot y-intercepts and x-intercepts, y-intercept, that occurs when x is 0. If you put 0 into this function, you're going to be left with a 2 on top, a negative 1 on bottom, which is negative 2. Back down here at the graph, negative 2 is your x-intercept. Excuse me, let me erase that because that's wrong. There we go, negative 2 here, y-intercept. It's already been a long day. The x-intercept comes from the numerator being 0, 3x plus 2, that's equal to 0 when x equals negative 2/3, and that's your x-intercept. Our second example, let's check out x squared minus 16 over x squared minus 7x plus 12. This function we can factor. The numerator is a difference of two squares, x plus 4, x minus 4. The denominator you can factor as x minus 4, x minus 3. Now your domain what values of x create 0 in the denominator? That's right, we don't want a 3, and we don't want a 4 either. If you use 3 or 4, it creates a 0 factor in your denominator. So our domain, all real numbers except 3 and 4. Don't forget the ones between 3 and 4, because those are equally important. You just don't want 3 or 4 themselves. Now if we go back up to the main problem, after it's factored, notice that these two will cancel each other, leaving us with x plus 4 over x minus 3. From these two factors in your denominator, that tells us a lot. That tells us that there's a vertical asymptote at the one that does not cancel so there's a vertical asymptote at 3. The one that cancels is the location of a hole. There's a hole where x minus 4 is 0. It's called a removable discontinuity. If you go back to the simplified fraction, the one that after you factor and cancel, and you plug a 4 in, you're going to get 8 on top and 1 on bottom. So the hole will occur at the x value of 4, but the y value will be at 8. That's how you find the location of the hole. I'm going to go ahead and put in the reduced one. Your graph's going to look like x plus 4 divided by x minus 3. I put my numerator and denominator in parentheses separately so that I know that I've captured the numerator before I hit the divide button. And now when I graph, I'm going to see a little vertical column of dead space when x is 3. You'll have to be careful that your graph will not show your hole on a standard viewing window. So let's see, let's go ahead and cover, notice the graph does flatten out on the far left and right side, so that means we have horizontal asymptote. The horizontal asymptote, and what we do for that one is we look at our dominant powers of x, top and bottom. Now those are both tied at 2, so we take our coefficients for those dominant terms. 1 over 1 is 1. Okay, so we've got domain. The difference between vertical asymptote and hole is whether you can cancel the factor in the denominator or not. Once you've located a hole, plug the x value into the reduced function, and that'll give you the y coordinate. Horizontal asymptote. Now, I will tell you, if the dominant power in the denominator is larger, like say that's an x cubed in the bottom, but only an x squared in the top, then your graph will flatten out at the x-axis where y is equal to 0. That's if the bottom outweighs the top. As long as those exponents tie, you use their coefficients as your horizontal asymptote. For this one, it was 1 over 1, which is 1. On the next slide, I'm actually going to graph this because I don't think I've got enough room to make it look halfway decent. No. All right, so I'm going to switch to another slide and graph this. Our horizontal asymptote was at 1. Okay, so where was our vertical asymptote? That was at 3. Our horizontal asymptote was at 1. If you plug 0 into the reduced fraction, you're going to get negative 4/3. 0 into your function gives you the y-intercept. Where the numerator, x plus 4, was equal to 0, that tells us that our x-intercept is going to be at negative 4. X plus 4 is equal to 0 when x is negative 4. Okay, so we've got a graph that's flat. It is really hard to graph these by hand on an iPad. And then in the upper right, we have that part of the graph. So it's not beautiful at all, but hopefully it's functionable enough for you to follow along. The hole, we had a hole at 4, 8, so I'm going to remove a tiny dot here, leave an open circle, and just label that 4, 8. There's a lot to keep up with, so you guys be patient with yourself. Feel free to use your graphing calculators as much as you need to. A lot of these problems have watch it buttons, so feel free to view those. Hopefully this video helps too. And I want to show you one more. It involves a case of the numerator having a dominant exponent that's larger than the one in the denominator. I'm going to try to keep this one fairly small, but enough to where you'll get the gist of it. X squared plus 1 over x plus 1. Now the numerator is a sum of squares, so it's not going to factor as x plus 1 times x minus 1 as you might think it would. So that's as reduced as we can go. The domain, any value of x, as long as it's not negative 1, negative 1 creates a 0 denominator. So that's our domain. Since we can't factor the numerator and cancel it out, it also represents a vertical asymptote. Remember, if you can cancel out the x plus 1 with a factor from the numerator, then it signifies where a hole is located, not a vertical asymptote. A hole is just a missing pixel, whereas a vertical asymptote is like an invisible barrier that your graph will not cross, and it actually most time will divert away from each other. Not every time. So domain, vertical asymptote, no hole. Now here's where, if you'll notice, the numerator has an x squared. The denominator only has an x to the first. In this situation, you have what's called an oblique or a slant asymptote. And the way to find it is to long divide. We've got x squared plus 1 for our numerator. Don't forget, if your dividend has a missing power and it's not consecutive, you have to put a 0 term in there. So we don't have an x to the first in the numerator, but we fill it in with a 0x. Now let's long divide. X goes into x squared, x times x plus 1. Change your signs. The first column adds up to 0. The second column gives us negative x. That's 0 minus negative 1. Bring down the next term, plus 1. And then we take x from out here, divide it into negative x. Negative x divided by x is negative 1. Negative 1 times the divisor, that's negative x minus 1. Change your signs, and we get a remainder of 2. You don't have to worry about the remainder when you're looking for a slant asymptote. You just need this part. Y equals x minus 1. How does that affect the graph? If you were to lightly sketch in the line y equals x minus 1, it would look like that. We have a vertical asymptote at negative 1. We have a slant asymptote along the line y equals x minus 1. We don't have a horizontal asymptote. We have a slant asymptote. You can't have both. To my knowledge, you can't have both. Now we're just ready to sketch it. So if you put this function into your calculator, let's see. Now I can tell you that there's going to be a y-intercept at positive 1. Because if you calculated f of 0, you would wind up with 1 over 1, which is 1. We can label that. The numerator, since it's a sum of squares, if you put that equal to 0, you're going to get plus or minus I. Those are imaginary numbers, so that tells us there's no x-intercept. Okay, so using your graphing calculator, what you should find is your graph will hug the oblique and vertical asymptotes, hug the oblique and the vertical asymptotes on this side too. But instead of the graph flattening out on the ends, it slants next to that imaginary line. And that's what the look of a slant asymptote would be.